He received the Bachelor and Master of Science and PhD degree in Electrical Engineering from Faculty of Electrical and Computing Engineering, University of Ljubljana, Slovenia. He is currently a full professor with Faculty of Electrical Engineering and the head of the Laboratory for Autonomous and Mobile Systems. His main research include adaptive, predictive, neurofuzzy, and fuzzy adaptive control system, and also involving system. Dr. Skorian is a Humboldt Research Fellow of Japan Society for the Promotion of Science and the Chair of Excellence at the University Carlos III of Madrid. He also served as an associate editor of Transaction Physicism and Transaction Neuroelectrical and others. Thank you very much for coming to this area.
Hola, ¿qué tal? So, I'm coming from Slovenia. I forgot to put an introductory map of Slovenia. It's in the middle of Europe. We are part of the European community. Ljubljana, where our university is the capital of Slovenia. Just 2 million people, 20,000 square kilometers, borders with Italy, Austria, Hungary, and Croatia. So we have part of Adriatic Sea, very nice coast, where you can go around the Adriatic Sea, sailing, for example, seeing beautiful Croatian islands. So that's where I live. So I'm coming from Faculty of Electrical Engineering. Doris said that I'm the head of the Laboratory for Autonomous Mobile System, which was true till 1 month ago, when we actually merged 2 laboratories. Merging is also the topic of my talk. So we merged 2 laboratories, Laboratory for Autonomous Mobile Systems and Laboratory for Modeling, Simulation and Control, in one laboratory, which is called now Laboratory of Control Systems and Cybernetics. So my main area is control, coming from control and trying to actually combine the techniques of computational intelligence into the control area and trying to do some applications to that area. So motivation for doing the research in this area is a number of new sensors which produce actually a bunch of new data, but so many data that we don't know what to do with them sometimes. And of course, we would like to extract the knowledge from those data, find information in a way to actually transform those data in some kind of more transparent and representative form, like it is given by models, for example. We will talk about data in the stream. So previous talk from Hillary was about batch processing, doing models from a certain sequence. But now I'm going to talk about online, on the fly, on the edge processing to use, online identification, online clustering. Why? Because we would like to have the model as soon as possible, without any delay in time, to have a possibility to operate, to use those models as soon as possible. What we are doing here, we actually trying to do recursive clustering, recursive identification of the models. We are observing the similarities and dissimilarities in the data which are coming from the stream. We are estimating the models from those data. We are talking about densities, membership functions, the typicalities, and of course everything because the data behave non-linearly. So we don't have a linear relation, which will mean that actually we can use all the techniques which are known from the identification, from the control area, identification of dynamical systems, identification of the systems in general, which is an old area. So we are trying to expand this to the nonlinear world. So something as a motivation for this work. We have two signals. This one with red crosses, blue circles, and which represent the signal X, and Y with the same signs. We have some special measurements with squares here and here, and from that we cannot see anything. We cannot find any relation. If we put this one against the other, we can see this. We can see that some of those samples are outside let's say normal behavior, which is presented with those two classes. And this kind of relation shows us that we have some kind of relation between the first process and the second process. So this is the basic motivation. Of course, just a simple school example. The outline of my talk will be the following. I will say something in this first part, let's say so, an introduction to the problem. I will explain what adaptive fuzzy models are, what are, in this context, evolving fuzzy models. And in the part 2, I will show some examples of evolving fuzzy model. We call it IFUMO. What is the basic algorithm? How did we detect faults using this kind of approach? How did we do soft sensing using this kind of approach? I will show you a self-tuning with 2 degrees of freedom control for so-called heliocrane system. And how can we do the 2D mapping in autonomous mobile system where you have to define the space where you are actually working. In the second part, I will describe the possibilistic clustering, where we extend the basic possibilistic clustering developed by Jim Carroll to the E-Cauchy and E-Gauss clustering. So it's again a modification and extension of known clustering techniques to the online world. So there is something about this basic algorithm and examples, and then again the control of using this kind of approach to control a simple laboratory plant. And at the end I will show you how we can detect the driver's actions from the raw signals which are already available in the car. So no new sensors, just the sensors which are already obtained to do what is actually the driver doing. How can we extend this knowledge? How can we add basic behaviors into the basis of those behaviors? So models, again, everywhere we are dealing with measurement, survey, technique in many disciplines. Most advanced, we all hear all the time about data mining, computational intelligence, artificial intelligence in many areas. And when we are trying to talk about models, I basically mean to dynamical models, not just a statical representation of input to the output, but dynamical models where you have also the feedback of the inputs, delayed inputs to define, to actually have a structure which is able to model the dynamical behavior, which is much more difficult because this means instability, it means problems with correlations of the signals. You know, if the delayed output is not delayed enough, then it will be very much correlated with the output itself. So this means additional numerical problems, and of course this should be also elaborated when dealing with this. And of course each modeling means definition of the structure of the model, and then on the other side also estimation of the model parameters. And this is so-called identification in control system theory. And of course, if you are building this kind of model, we should have one test set also to first see if the model is properly structured, properly, as the parameters are properly estimated, and then of course you have to validate this model on another bench of data to see the model is really acting properly also on the fresh new data. And how to use those models. What are the applications of those models? So we can use them just for one step ahead prediction, to predict the future recursively, then nested loops. We can predict more steps ahead. We can, of course, use this observed output and put it back and have a simulation. Here you see that we just use the measured outputs. And if you do the inside loop of this delayed outputs, we can do this, we call this a simulation use of the model. We can, of course, use this kind of model to optimize a certain strategy of control. We can do some kind of analysis to try to see what is going on if the process is actually excited with different input signals, what will happen in the system then. We can use it directly for the control. Model-based predictive control is one of the important techniques using models, also nonlinear models, fuzzy models, neural models, and so on. And important area is a fault detection, monitoring of the system, trying to find the faults, detect them, isolate them. Means that we would try to model a nominal, normal operation of the system to find one model, and then finding the models by expert, trying to model also the models for the faults, all faults which are actually happening. And then we will just do the comparison of current operation of the process with those outputs from the nominal model and the models with faults. And we will try to see which one is closest, and this one will somehow show us where the possible error is. So, fuzzy model identification means then structural identification plus parameter identification. And we have different paradigms for that. We have classical way of doing narrow fuzzy models with constant fuzzy partitioning and constant local model parameters. One possible way. Then we have adaptive way of doing this. It's adaptive fuzzy partitioning and adaptive local parameters. So we are changing the clusters, membership functions, and also changing the parameters of the model. But we don't add new models into the whole model, new local models, let's say. This can be done with additional incremental, adding clusters or new rules or new models into the model, and we are calling this kind of approach incremental approach. So adaptive fuzzy partitioning, adaptive local model parameters, and adding of the rules or local models. This is just adding. We can do this much more sophisticated. We can do this by adding. We can merge certain rules or certain clusters if we talk about neural fuzzy model. We can split certain clusters where the model is not appropriate, or we can remove the clusters from the model. So remove, on the other side, the rules from the model. I'm talking about this kind of neural fuzzy model. We have inputs, we have output, we have membership functions, we have input to those membership functions. This input vector goes also to the local linear models, and each local model is weighted with the membership value and added to the last summation, where we get the whole output of the model. So the whole output is actually the weighted sum of local linear models. First one till m and local linear model. Why local linear models? It could be also something different, because they have also good extrapolation, those kind of models, and the control is easier. So we can do, this is proven as a universal approximator. So with adapting of the structure, we can always find a certain tolerance factor where our error at the end will be. So, if it is a universal with local linear models, then why not use local linear models? Because from this control perspective, it's always much easier to do something further. All the techniques were actually developed, and control were developed in a linear space. So, fuzzy model with constant fuzzy partitioning and adaptive consequence parameters and constant number of rules. This is one way of adaptive fuzzy models. So, this division of partitioning of the space, of the input space, is constant, and we are just changing the local linear parameters of all those local models. We actually this kind of approach is used for different adaptive control purposes. We did some adaptive controls of different systems, published in those papers. We also proved the global stability of this kind of direct fuzzy model reference adaptive control, and which is important. In control, you will always have to prove that the system is stable. So, a lot in this case, because it's a complicated system, a lot of work should be done to prove the stability. Otherwise, nobody will publish this. If you are talking just about publishing. So another possibility is adaptive fuzzy partitioning and adaptive consequence parameters and constant number of rules. So these parts remain the same, the number of them remain the same, but now we are changing also the membership values. We are shifting those membership values around the input space. And of course, additionally, we are also changing the parameters of the local linear models. Sometimes, again, in control is not a very pleasant thing to change too much things. That's why the first approach is, in that sense, much more reliable, much more robust, and of course, this can cause additional problems. In this sense, to have an adaptive fuzzy partition, adaptive consequence parameters, we did the recursivation of the C-means clustering, and also the recursivation of Gustafsson-Kessel algorithm, which was actually the basis to further develop the evolving fuzzy systems. And this is now the scheme of evolving fuzzy system. So all those things are changeable, and also the number of rules, which is here given by this M, is changed. So if somebody is interested about that, you can find a survey about those systems called evolving fuzzy and neurofuzzy approaches in clustering, regression, and identification and classification in Information Science Review. So this is now changed in all dimensions. Maybe sometimes, again, a very complicated structure should be reduced to some parts. So some basics about evolving fuzzy models. The basic thing is similarity between the measurements which are coming from the stream. So I have to say again that we are talking about samples coming in a sequence from the stream, and usually we are trying to define centers of clusters, which are given here with Vi and V2, and we are trying to find the distance of current observation, current measurements given by this Z at time k, and we are trying to find the distances. And of course, you know, from the computational area, you can find those differences in many different ways. the most simple is Euclidean distance, just reducing this scalar vector, this product, or Mahalanobis distance, where you use an inner matrix, which is usually inverse of the covariance matrix of the cluster. We will talk about that later. And it gives you the normalized measure, normalized in each direction with the variances in that direction. So we should define the distances of the measurement from the prototypes of the clusters. Those measurements are just basis for calculation of the degrees of similarity, typicality, likelihood, however you would like to call this. So the basic membership degree is defined like this. So this is the way how in the C-means clustering the membership is defined. We just inverse value of the distances between those two points squared, and this means the membership degree. Talking about the Gaussian distribution, typicality is defined with this gamma, and this is e on power minus d on square. So distance is an exponent in the exponential function. Or the Cauchy distribution, there also the typicality is defined, which is defined like this. So if the distance is 0, this is 1, this is also 1, so the typicality of 1 is the biggest, typicality of 0 is the lowest. This has a problem. If the distance is 0, this goes to infinity. So here we have to be careful with dealing with this. Those similarities are usually normalized. So similarity of this sample to many centers has different unnormalized memberships. And usually we are using them normalized, so each one is normalized by the sum of all unnormalized memberships. And we can also use the techniques which do not normalize the degree. So we are talking about absolute degree and the relative one. And I was talking about actually about the point as a prototype. So we are calculating the distance here. And distance from the point. The prototype can be also different, not just the point. It could be a line or a hyperplane in general, talking about more-dimensional space. And we can define the distance between the prototype and the current sample as a distance between this point to the line here. So this is the way when the prototypes are not only points in the data space, but also some other features. Now, how does it look, the basic evolving mechanism? So, as I told you, we are adding new clusters, we are adapting old clusters, we are merging clusters, we are splitting clusters, and we are removing clusters. So when new input data arise, we have to decide what to do with this sample, where to put it, in which cluster. So if the density or typicality, if the typicality of the current measured cluster is above a certain level, which should be defined, then we can add this sample to the existing cluster with the highest typicality, highest membership. If this is not true, of course, this means that this input data, input sample does not belong to the existing cluster, and we have to add a new cluster. This means evolving mechanism. We are adding a new cluster. If it belongs to some of them with higher density typicality similarity, then we will just adopt this. We will put this to 1 or we will adopt the clusters accordingly. So adaptation. And then, of course, we are running this with new inputs. So adding a new cluster, we have a new area where we actually haven't identified nothing. This is meant as a regression problem. This is y, this is u, this is the line which actually represents where the most data are. We already identified this region, then we are starting to go into the new region with new, we maybe got the data here. It means that it doesn't belong to this cluster. We have to form a new one. And of course, at the beginning, it's difficult to have a right shape of the cluster. With some new samples, we will adapt this cluster to get a proper shape of this by adaptation of this current cluster. Of course, this is not always the same. We can, for example, have a data here, and this is learning area, we have a data here, and of course, if we are calculating the distances and the membership degrees, this one belongs to all centers. And we can calculate the memberships to all centers. And we can change all the clusters. So this means that actually all clusters are changed accordingly to the membership degrees. So it's a weighted, let's say weighted adaptation. So if this belongs with 0.8 according to the calculation, and this one 0.2, then of course this center will be moved, weighted to this 0.8 weight according to the membership degree. But this is not always the case. This means sometimes troubles. In regression, this is the problem. Because you will change also the clusters which are far away, always, because you will always have a certain membership to all the centers. That's why sometimes this kind of winner takes all adaptation is used. So we will calculate again the membership degrees, the typicalities, and we will change only the winning cluster. The winning one is the one which has the typicality which is above the threshold, and of course the maximum one. So this was adaptation of the clusters, and of course it can happen because one thing I forgot to mention is that we can get the data stream from different processes in a sequence. So it's not necessary to have one, to have the old samples from one process and then from the another one. You can have in a sequence samples from different processes, and this will happen that you can get clusters which are close, very similar, but you have two clusters, and then of course redundant structure, and you would like to merge those two because they have actually present the same behavior. This can be done in many different ways in evolving fuzzy modeling. You can calculate the correlation coefficient between the membership degrees of those clusters, and if they are very similar, then you can combine this, but you have to store all those memberships, which is not good. So evolving means to store only the parameters of the models and, of course, of the clusters. Means covariance matrix, centers, and number of centers in the clusters. We don't store all the data, otherwise it won't be usable for big data analysis and mining. So we can calculate the angle between the principal eigenvectors of both clusters. So principal eigenvectors can be calculated through the covariance matrices, and you see that here the angle is 0. So centers are close, we can combine those two clusters. We can calculate Lagrange distance between the clusters. So distance, which is weighted with inner norms depending on the covariance matrices, once calculated with one covariance matrix with one cluster, once with another, and trying to see if this relates. And what I will show you here, it's volume-based merging, which is our last research, let's say, which actually gives a few new aspects to the clustering because it gives you a really good tool to do this. So when we are merging, we're just then making a cluster which will cover, in this sense, both regions together. Yeah, and the volume of the cluster depends on the covariance matrix. It's actually the determinant of the covariance matrix. This is proportional to the volume. So the volume of this cluster, the area of this ellipsoid, it's given by this formula. So it's a product of eigenvalues of the covariance matrix. We should do the singular value decomposition of the covariance matrix to obtain the eigenvectors, eigenvalues, and product of those eigenvalues is an area, not just directly. It's multiplied by this term here, by a gamma function, and so on. And each cluster, as I told you, for each cluster we should remember, we should store the center, covariance matrix, and the number of the clusters. So if we have all those data for all clusters, then we can also actually calculate precisely the shape of this merged area. How? So we are calculating the mean of the cluster from the whole, so we are just storing the mean. We can calculate the covariance matrix, and covariance matrix via single value decomposition will gives you a matrix of eigenvectors, eigenvalues, and transposed eigenvectors. Where this M is a diagonal matrix of means, and D is a unity matrix of these dimensions. So, and then we can get from those values here, from lambda, we can go to the volume. Further on, so if we look, if we want to calculate the covariance matrix of the merged one, we have to use, of course, both data from the first, from I cluster, and from the second one, from the J cluster. And this means that we have to calculate this transpose. And this is just this term, Zi transpose Zi plus this one. And we know that if we store the covariance matrix of the first and centers, then we can restore this back, the data in this transposed form. And this one also. So just with those information about the covariance matrix and the centers, we can get a perfect reconstruction of perfect merging of the new cluster here. What does it mean? So we have to calculate weightedly, in a weighted way, a new center. So we are weighting the first center with the number of data, second center with number of data inside, and divide this with the whole number of data. This is I. And then we can calculate the new covariance matrix of the merged clusters. And when we'll do this, we'll do this one, this empty space. So this is the whole one, this is the first, this is the second, and then these holes are the problem. How can we define the holes? Easily, we just have to find the ratio between the volume of the whole space and the volume of the sum of both volumes. And if this is less than prescribed value, then we will merge. And this it doesn't mean that those phones should be like this. The second cluster can be also like this. And you will get this kind of merged cluster, and you will get another holes or space which is not covered by which is not covered by the data. So let me show this. So what we're doing, we are putting the threshold for the merging. We initialize this merging procedure. We compute volumes for all clusters. We merge them, and then we see if this ratio is small enough to have enough overlapping to put all those things together. So if the minimal ratio is less than prescribed threshold for joining, then we will merge the clusters. We will change the number of clusters for one and finish this routine. Look at this example, very simple screw example with join threshold, which is equal 1.1, means that we actually want to have very fine definition of the clusters, and you see those clusters like this. A lot of clusters, a lot of centers, and each cluster has a border with 3 sigma control around. If we do make a bigger, so to have a more rough separation of the clusters, you will find the distribution like this. 2 clusters with centers which are very equal, and the orientation of the clusters in this way. What is actually this idea now imposing? It's actually imposing that it would be nice to do the small granules, which are easy to find, each one with the covariance matrix center and the number, and then we will just combine them to find the bigger, more complicated structure, which means that we can find very different shapes. Otherwise, if you are going from big to small, it's this much more difficult. So going from small granules and put them together with this simple and efficient algorithm. Yeah, this was merging, so very important part. Splitting again, if we are talking about regression problem, you can get this kind of cluster according to the specified thresholds, and you will see that if the curve is like this, not seen very good, but approximation error will give you too big error, and then you will try to split this cluster to first to 2 new clusters, which is much more non-efficient task, because if we are talking about evolving strategy, you just have a center and covariance matrix and no data itself. So we cannot reconstruct the behavior to be like this, to have it here and here. We just have to split in this principal dimension or principal component to put this center into 2 according to and the coordinates will be according to this principal component. And of course, after that, with new samples, we can learn the right behavior. And of course, when we have a cluster with very small number, a lot of time, no happening, it was formed a long time ago and nothing happened, then with small number of samples, then we can remove this kind of cluster. We are talking about the ratio between age and support area, where H is the number of samples between the first and the current sample, and the support area is the number of samples in this cluster. So this was the first part of this basics about evolving linear fuzzy systems. And now I'm going to talk about one specific version of that called IFUMO, to show a basic algorithm and fault detection problem and soft sensing. So more in application way to do this kind of approaches. So IFUMO means evolving fuzzy model, apparently. So this is based on recursive fuzzy clustering. In a, let's say it's a modification of C-means clustering. Here we have to calculate the fuzzy centers and fuzzy covariance matrices. What does it mean? It means that we are calculating the centers of the clusters in a fuzzy manner. So we are modifying all the centers. This is done analytically, so to change the previous cluster with a new sample to obtain a new one, here on the left side, where we add this error between the cluster center, previous one, and the new sample, and we actually weight it with inverse value of sum of all membership degrees. This is a weighted change of new cluster value, cluster center. Filtered sum means that we actually forget old values of the sum and add this current membership degree. Why we are waiting? Why we are forgetting the old one? Because we are starting with very far from the real center. And we have to actually forget the old one to reach the right way. This is somehow problematic, of course, because we are starting it completely differently, because we are changing all the membership, all the centers. That's the problem. And the same is done for the fuzzy covariance matrix. It's again fuzzified and forgetted previous values. When we do this, we have a partitioning of the space. Using center and covariance matrix, we partition the space. We have the center in the data space and the covariance matrix around. And of course, we can find the membership for each sample which is coming. And of course, on the other side, we have to define the linear parameters on the output side. And we are doing this with local model identification. So weighted recursive least squares algorithm. And we did this for the wastewater treatment plant. This kind of approach with adding, removing, merging, and splitting of the clusters, we can do. We did the fault detection and soft sensing in the case of water waste treatment plant, wastewater treatment plant. So it's nearby in Slovenia. This is a picture from the air, from the drone. And what is the problem with those processes? They are time variant. The processes changes according to the weather, season, rain, hot period. Then the disturbances are very different. You have celebration days, holidays, so high variety of incoming water, high variety in ammonia and so on. A lot of dirt, mud and so on. So frequent failure of sensors. So if you want to, for example, do the aeration in the tanks, in the pools, you have to control the concentration of oxygen in the tank. So these are the pools, you see. I put it here tank, it could be also tank. This is the first one, the second one. Here is the inflow of ammonia, and here is the airflow inside to the second tank, where you have the aeration. So you're putting air with oxygen to remove the dirt and to do the aeration, so-called aeration process. So here we have a position of the valve, so we can define the position of the valve to put enough air inside this second pool to have the proper aeration in this. And of course, this sensor of oxygen sometimes fail out. And of course, the whole regulation of the input air depends on this sensor. So the idea was to make a soft sensor which will, in the case of failure of sensor for oxygen, for air here, will reconstruct from the other data the concentration of oxygen inside. So we did actually realize this with two IFUMA models. First one, we defined the relation between valve position and the airflow, because also here can happen something with the valve. Then this concentration of O2, of oxygen here, depends on the airflow and the temperature outside. So again, very different temperatures, very different airflows, another IFUMA model to define this relation. Of course, the first one can be seen as a statical model because we just actually do the transformation from the valve position. There's no feedback inside this process. But here, of course, we have a feedback of O2 concentration to properly model this part of the system. So first one is a statical model, statically IFUMA, and the second one is dynamical. And this one is much more complicated. So first we did this, let's say, fault detection for the valve. So if valve is open on a certain level, you should have a certain airflow. Otherwise, something is wrong. So we just did this relation. We modeled this relation, and if something happened with this, if the difference between the proper function of the airflow obtained from the model and the current airflow is different from prescribed one, then we will have an alarm here. And this one is much more demanding and complicated. So we are trying to find out what is going on with concentration of oxygen. So the blue line, blue curve, is the measured concentration. The black is measured concentration with fault, and the sensor output with dashed red line. So the first part here was learning period. You have to learn the sensors, learn the models, and then you can see that we can perfectly follow the measured concentration. And here we have measurement failure. So the sensor was failed, and this was the real. This was the real, because we put another additional sensors to do additional measurements. This black was the real concentration, and our reconstruction is given by dashed red line. So we could reconstruct the O2 concentration, although this measurement, which is most demanding, and the right one, let's say, this one, which is of crucial importance, although this was not available. So we did this from the other sensors, from other variables, actually. And this was like alarms actually were fired. So this was this learning area where you see we have some alarms, false alarms, but after some learning, you can see that, for example, this is the number of clusters in both models for airflow and for O2. Sorry. After learning phase, we got 5 clusters, 5 models, 6, then merged to 6 again, and then finally 7 clusters, 7 rows for first model, and here again some combination or merging to 2 clusters in there, two models, linear models again. But the most important is that we don't get any false alarms, and we can get very fast notice about the fault. We did also some control approaches, control of heliocrane with 2 degrees of freedom, which means that we have 2 controls. First is feed forward, going from the reference to the control signal, actually producing or compensating the operating point. And the other one is given as a feedback controller, actually acting on the reference, control error here. And we did this in a way to actually identify the modeling as a full model, and we add here a fuzzy model-based predictive control as a feedback controller. So we have all these procedures, adding new samples, regression vector. You can see that here we have a regression vector to use the recursive identification. We have 1 because of the offset, we have U because of the control signal, and we have delayed output because we are predicting 1 step ahead of the output. We did this from the scratch, so the system learned everything from the scratch, adding mechanism, removing mechanism, and defining the controller. You can see the reference and the output signal, not much difference, and the control action, which is very different, so it means that the system should be very much nonlinear. We did this approach with linear cluster prototypes. So as I mentioned, that the centers of the clusters or prototypes of the clusters, it's not necessary to be just the points. They could be also the line. And this is very much interesting in special cases. So we are defining the difference from this distance from this point to the line as given here, as a scalar product and normalized. And then the membership degrees can be calculated as given here. So this is given in this paper, which will be published now in the IEEE section fuzzy systems. This was the way how we did actually define those 2 lines, which define the process here. But more important is this example. It's a 2D measurement from the laser range finder. You know, we deal with AGVs, which are equipped with laser scanners, lidars, and we are trying to observe the space where this AGV is moving. So doing the laser scans, and this is one laser scan in one environment. These are the points obtained from the laser scanner. And of course, we would like to find the shapes, where we are, then localization problems, but first we have to do the mapping. And this was the basic idea. Why not to find those shapes in the space with clustering where the prototypes are lines? Because it's the most natural. So we try to find the line, and try to find the differences from that line of the current observed sample. And we did this with the proposed IFUMA with prototype with a line, and we've got this kind of result. With 1 line here, which actually corresponds to those samples. here is missing because we have just 2 samples here and we miss this part. That's the problem of an algorithm and we have to improve it. But all important points are modeled with proper lines, and we can reconstruct this kind of model very easily because we have a center and we have the parameters of the line. And the line is defined, and also the size of the line with covariance matrix. And we did this with other techniques which are known from the fuzzy world. We did this with Gustafsson-Kessel algorithm, where first you have to define the number of clusters which are you searching for. So that's the problem. In our case, in evolving, you are adding new clusters, and you don't need to know how many clusters you will actually obtain. Here you have to define the number of clusters. And first, we define the proper number of clusters, which is 13. And see, we found those parts very good, but there are some parts which are problematic for Gustafsson-Kessel algorithm. And of course, if you don't know the right number, you will get a completely different situation. So, in that cases, this kind of prototypes with lines are much useful. And something about another technique which is called possibilistic clustering. Actually, I put this because of Jim Keller, but he's not here. So. Because he's the one who actually discovered the algorithm of possibilistic clustering, possibilistic fuzzy clustering, where you have actually this kind of way to calculate. He called this typicalities. So typical value for each measurement according to the certain center. And if you have the Cauchy density, Cauchy distribution, then talking about the densities of the sample, if you want to calculate the density of the sample, you will calculate all the distances to the samples which are inside certain clusters. So the density of this point, according to the Cauchy distribution, means that we should calculate this term, means calculate all the distances from the observed sample to the samples inside the cluster, do the averaging, so dividing by the number of samples, and calculate this term. This is the way how it is calculated in a batch when you have accessibility to all the samples. But in the evolving system, we don't have it. So the same calculation for current samples mean that we put somehow the information about the samples into the center, and we can calculate the same typicality. This is the same, just modified for the concurrent calculation, for recursive calculation. So we just have to, store the center of those data here inside this region. So as said, this is mean, and we could, of course, add some kind of inner norm to make this density more suitable for different problems. And for example, this is done in this paper, inner matrix norms in evolving Cauchy possibilistic clustering for classification and regression from data streams. So here we discuss how this inner norm should be used to be capable to elaborate different problems. And we did actually do cyber attack monitoring using this kind of forms. Maybe you remember this distance. If we just talk about those brackets and this inner norm, it could be seen as a Mahalanobis norm if this is inverse of covariance matrix. You see this term T2, with this index, which is in this case defined as trace of A multiplied by covariance matrix of this cluster. And if A is equal covariance on inverse of the covariance, this is then unit matrix. So trace of unit matrix is equal to the dimensionality of the space. So this is then constant almost, and equal to the dimensionality of the space. So this typicality actually will tend, if the sample is inside the center of the cluster, will tend to the maximal typicality of 1 against 1 plus t. But this is not so important, just to have an idea. So this is the Cauchy density, calculation of Cauchy density, which is very useful for observing those phenomena. And the second one is Gauss density. So we use this Mahalanobis norm as an exponential term to calculate the typicality. And now we don't actually calculate the centers, covariance matrices in a way of fuzzy calculation, but we are using a principle winner takes all. So we will calculate the error between the current center prototype of the cluster and the current measurement. We will change, this is exact change of the variance center, where the new one is the old one plus 1 against n plus 1 and this error. And the covariance matrix is again calculated precisely according, because there's no weighting of that. So each sample to this cluster and new calculation of all those terms which are necessary. Of course, we are going from the sample. First, at the beginning, you cannot calculate Mahalanobis distance because Mahalanobis distance has covariance matrix on -1, so inverse of the covariance. At the beginning, could be singular. It's a problem. So at the beginning, when you get the first few sensors, you should calculate this with Euclidean distance, which is where you calculate, no problems. And after that, Mahalanobis distance has certain advantages because you can distinguish between different shapes of clusters. You can then calculate the typicality, and then you do the choice of maximal typicality. If this maximal